All right, let's start talking about section 5.1. It's got to do with area. We've been talking about antiderivatives, and we're talking about the idea of a graph, the area under a graph of a function, area under a curve. If you hear that phrase, it'll be coming up a bunch. And what does it mean? Well, let's take a look at an example here. And I think this example helps clarify things. I think it was a good one for me. I'm going to take you over to my iPad and take a look at a couple of graphs I want to talk through and actually show the area under a curve and get a clear picture of what that's kind of referring to. All right, let's start with up at the top right on this iPad right now. If I've got time in seconds along the x-axis down here and the velocity in feet per second up the y-axis, okay, in this direction. And if you were traveling, starting right now and you were already moving at time 0, you were moving 30 feet per second, and you maintain that for a full 8 seconds, okay? So a full 8 seconds, pardon my drawing there, all right? Then you can recognize what we've got here is when you multiply the height of this, it's 30, by the width 8, you've actually got the velocity times the time is the distance. The area under this curve is the distance traveled. This velocity across the top here, you maintain the velocity. The graph is the actual rate of change. And you maintain that for 8 seconds, and you've got the distance, the amount of rate of change that happened, amount that accumulated over those 8 seconds. And so in this case, we've got the velocity was 30 feet per second, and then multiply that times the 8 seconds, and you end up with 240 feet. You know, that's feet per second, and then it's times seconds, and the seconds units cancel, and you end up with 240 feet. So this area underneath the curve is actually the distance traveled when rate of change is the graph that you're looking at, okay? So there's an image I wanted to give you now, and go over to the top left graph here where we've got time again in seconds and velocity on the y-axis. I want to show you what we're doing. There's some, whether it's a vehicle or a bicycle or whatever, somebody's utilizing, they are moving along. And the rate of change, they're starting with it. Time 0 seconds, they're starting at 20 feet per second, okay? And then every 2 seconds, it's measured. Every 2 seconds, the rate of change is measured. So at 0 time, it's starting at 20 seconds, at 20 feet per second. At 2 seconds, 30 feet per second, then 38, then 44, then 48, and then 50 seconds. And so you've got this curve that's growing like this, but it's not nice and flat and rectangular. The shapes are not rectangular, so it's kind of hard to get the distance, gauge the distance traveled in this situation. So I think I like this explanation. I think this is a good one. And so what's been done, now that we've been talking about limits and you've got that under the belt a little bit, let's look at this situation right here and utilize that. Watch what's happening here. If I trying to estimate how far are we going, if I knew it was going to be a low estimate. In other words, if I draw rectangles every 2 seconds, and the height of it be the bottom of the curve, okay? I know I'm low, okay? So this first one is 20 high. The second one is 30 high. This third one is 38 high. The next one's 44. And this last one is 48 high, okay? And so the sum of these areas is going to be, and this is on the low side, so this is going to be a low estimate, the low estimate. And if I take the area of these rectangles, I'll be approximating it. So I've got 2 times 20 plus, what is the next one? Oh, and they're all 2 wide, 2 times 30 plus 2 times 38, plus 2 times 44, plus 2 times 48. All right? The low estimate is this value. And what do we get here? I'm going to add the numbers up and let's factor out a 2. I've got 50, 88, 132, 180. Yes, that's 180. So that the sum of those rectangles is 360. So the low estimate on how far this distance is 360 feet. Now let's go for a high estimate, all right? And this time we'll start at the top right of each rectangle and have it be so that it touches at the top. It just touches the top of the rectangle all the way across, okay, and just goes across. And now all of the time, this is the area now that we're looking at. The area of this that I'm shading in is the area of these rectangles all the way through, all right? Now what we've got is, this is a high estimate because every one of them is higher than we actually went. But we've got 2 times 30 this time is the top, is the bottom, the lowest rectangle. Then we've got plus 2 times 38, plus 2 times 44, plus 2 times 48, plus 2 times 50. All right? And that is, what do we have? 30, 68, 112, 160, 210. Factor out a 2 times 210, and we've got 410 feet traveled. Is the high estimate. It's somewhere between 360 and 410 feet. Well, notice this. If we add up off to the side here, the difference, make this 2 wide, okay, and get the distance, you know, all of these little rectangles is the amount of error that's in between the low guess and the high guess. And if we add all those up, you notice it's going from 20 at the bottom up to 50. So this is 30 on the side and it's 2 wide. So the area is 60. So we're about 60 feet error it's off between the high guess and the low guess, okay? Now check this out. I think this is kind of cool. So, and this is where some of these guys finding this out and applying it to calculus is kind of wonderful. It's really kind of cool. All right, now check this out. So what happens if we make the width a little bit smaller? Let's cut it in half, all right? I'm gonna go down here in the bottom, and this time we've got this curve, all right? And this time we're gonna cut it in every second instead. The low guess is there. We're going over from the base every time and hit it there. And I think this makes kind of a cool point. So that this is, and then this low base here. We're doing every, oops, excuse me. We're going from here over, right? So I'm going over to halfway. And then I'm going over from here halfway. And from here halfway, and from here the rest of the way. Okay, so now that's the low guess, whatever it is, you know, whatever those values are, we don't have the increments, the halfway in between marks, but we do know this down here is 20 and this is 50 on top. Now we go with the high guess, the same thing, okay? The high guess situation. So I'm gonna go here, down, you know, all the way across. All right, and notice that these areas, look how much smaller the area of these regions are becoming because it's only 1 wide. So look at the difference. We're going from 20 up to 50 again. So we've got a rectangle over here, but it's only 1 wide this time, right? It's still 30, but it's only 1 wide. So this error now from here to here is actually only 30. All right, you see what I'm saying there? All right, now look what happens, that's the amount of error. Now what happens if I go to a half a second? Okay, that's 15 feet error. A tenth of a second, a hundredth of a second. 1,000th of a second. It's getting smaller and smaller and smaller and smaller, all right? And as it's getting smaller and smaller and smaller and smaller, this is getting less and less error to the point that this becomes actually a smooth curve. When you keep getting it smaller and smaller and smaller, it's getting real teeny. It's 100th of a second wide times 30, so it's 30 hundredths, okay? And then you get it smaller and smaller and smaller and smaller. All right, so it's getting smaller, and eventually it gets so that it's a smooth curve instead of all the rectangles, okay? So it turns out the area of that, the area underneath that curve is the distance traveled. And when we take the limit of those rectangles, the area of those rectangles, it turns out to be the area under the curve. And an example of it, let's look what happens here, that if we've got a situation where, let's say you're on a bike or something, and I'm on the bottom right curve graph here, and we start at 0 seconds, this is time again, and this is velocity up here. So we're at 0 seconds, and then we somehow miraculously get a steady increase. All for 3 seconds, we stay steady. And at the end of 3 seconds, we're going 15 feet per second. And it's a steady increase. You know, that's not very likely. But at the same time, we're going to say that, let's say you did that. Notice what happens here. We've got ourselves an area that we can actually measure. Okay? And I'm going to show you, we're going to talk about this shortly. How do we use an integration technique to get this value? And let's take a look here. This is a rectangle, it's a triangle, which is 15 high and 3 wide. So the area equals 1/2 base times height equals 1/2 the base is 3 and the height is 15. So that gives us 45 divided by 2, which is 22.5. And in actuality, we've got ourselves a little equation this time that we can use for this function. And notice what it is. The rate of change is the slope, the y-intercept is 0. The change in y is 15 over the change in x is 3. So the slope equals change in y over change in x, which is 15 over 3, which is 5. So the slope is 5, and this is time. So the equation is 5t there. Now, shortly we're going to talk about taking, when you integrate 5t between 0 and 3, what do you get? The area under the curve is said to be this. We're going to talk about that. We'll do that in class. We'll do it ourselves in a little bit. Check it out yourself if you already know how to do that on a calculator. We're going to practice it. We're going to get it down, and you'll be confident with it. Area under the curve is the antiderivative. It's the integration of the function that makes the graph, the area under the curve of that function. That's kind of an interesting little moment there, okay? We're going to talk about that more and more. The area under the curve is actually the distance traveled when we've got a rate of change going across the top. Okay, we'll come back to this. I wanted to get that across to you. We'll refer to that again, and we'll talk about it soon.